Okay, let's start our lecture number 21. This, in fact, starts the last part of this course. We have divided the course in 6 parts, so that would be the 6th part. And this one is the last part, the set of 4 lectures that compose the 6th part of the course. Today we are going to establish the connection between source and field. So what are the equations that govern the propagation of an electromagnetic wave, and how do we connect that information with the amount of charge density, time rate of change of the density, how do we connect with the current density and so forth. So we are going to talk about how to handle this problem in a formal way. We are going to revisit now a generalization of potentials. So these are the electromagnetic potentials. They are the intermediate quantities that are used to determine the final quantity. Then we are going to derive the non-homogeneous wave equation. In fact, we are going to talk about both in the not only Lorentz gauge, but also in Coulomb gauge. I forgot to add that here. Okay, let me just rewrite here. We're going to do that in both gauges, in both frameworks. Let me just put this down here. So that's going to be in the Coulomb gauge. We are going to derive the solution formally, the Coulomb gauge, and in the Lorentz gauge. And finally, we are going to derive the general solution for the non-homogeneous wave equation in the Lorentz gauge. We're going to obtain also the solution in the Coulomb gauge, but we're going to do more specifically, in fact, we are going to talk about the Green's function for the non-homogeneous wave equation in the Lorentz gauge. Then we are going to derive the general solution when we have an unbound region. References for this lecture: Jackson's Classical Electrodynamics, sections 6.1 through 6.5, and our ebook, sections 11.1 through 11.4. Just reminding you, some who are catching this lecture in the middle, I mean, there are 20 classes before, the 20 lectures prior to this one. So some people just visit and see this lecture, I mean in the middle of it. So the ebook can be found at this address, lsi.ufpe.br/Fontana. Go and search for Electromagnetismo in Portuguese. Then you have part 1, part 2. When you find that link, you open it. Electromagnetism part 1 will have chapters 1 through 5, and part 2 is going to have chapters 6 through 11. And we are talking about the last chapter of part 2 of the ebook. Okay. So our aim is to connect the charge and current fluctuations with the fields they produce. So we are talking about, in fact, radiation, right? So good examples of electromagnetic radiators are antennas, well known, right? These are dipole antennas, just a piece of wire, straight wire. A transmission line, you end the transmission line with, you open one terminal and the other one, make two wires, you have a dipole antenna. Or a single piece of wire, if you want. Just fix this thing here. This is class notes of the next lecture. I'm gonna erase it. And this one too. So let me just get rid of this and put some more pages here so you can do some scratching. Also a piece of wire, a broadcast antenna that you can see in some of those TV stations and radio stations. You just have a single on the earth, right? On the ground, you have a piece of wire. To do that, you have to put a tower holding that thing, Then you have an antenna there. You have other examples, the loop antenna that we have, sometimes FM antenna for catching TV signals. We have this type of antenna, loop antenna for higher frequencies. This is a pyramidal horn in which we can have energy coming out of a waveguide, then radiates. Or you can go the other way, you can detect radiation. Sometimes you can see in a parabolic, you have a parabolic concentrator antenna, parabolic antenna. In the middle, you're going to have a pyramidal horn that's going to catch the information. So the incoming, let's say, radiation is focused down to the focus of the paraboloid, and you have a pyramidal horn right here, okay, to catch the radiation coming to the parabolic antenna. We have this type of antenna, and also the monopole antenna just drew to you, okay, just a piece of wire. Also have an important principle in which establishes if you determine the radiation properties of a given radiator, that radiator is going to be the same properties relative to the reception of radiation. So this is a very general principle. We are not going to go through that, but you can demonstrate, you can put that into an equation. You can use that principle. Once you establish the radiation pattern of an antenna, you can determine the detection pattern of the antenna directly. Okay, that's the reciprocity principle. We are not going through that. I mean, we have a course lecture in our program, in our graduate program, which is antennas, in fact. So it's taught here in our graduate program. So we have an entire course dedicated to that subject. And also it's important to determine how electromagnetic waves interact with surfaces or objects, okay? So objects might behave like small antennas. So all the formulation we are deriving here is useful for this type of additional situations. You might have scattering by an object that has small size relative to the wavelength, for instance. We can analyze that. There are different scattering regimes we can look at. So we have interaction, okay, with irregular surfaces, with screens. We have diffraction, a partial block passage of electromagnetic wave through a screen. We can sometimes model surfaces, irregular surface, as current sources. So I mean, you can use these things we are talking about here in other situations. The most tangible ones are those related to antennas, right? We have antennas. So we have a current source or charge fluctuation that emits some radiation. We want to make that connection. So the solution for the radiation field obviously is going to be now is no longer a homogeneous solution, right? Before we said, well, we have fluctuation, charge fluctuation here. We want to observe the effect far away, right? In this region here, we don't have charge, we don't have current, right? Now we want to consider the inclusion of the current and the charges, right? So in doing that, we are going to deal with electromagnetic potentials. Let's consider that we have linear, homogeneous, and isotropic media, so we can establish simple differential equations. Otherwise, it might be very complicated, right? Depends on the medium. In general, we are propagating waves in vacuum, in the atmosphere. We can consider, to a first approximation, that the properties of the atmosphere do not change a lot. They can be represented by a homogeneous permittivity and permeability. Obviously, if they have rain, have other things, pollutants in the atmosphere, then we have to consider fluctuations in the property, but that's a more specific situation. Now we consider linear, homogeneous, and isotropic media. Just recall that in electrostatics, we use potential functions as those intermediate functions to solve for the final quantity, which is the field. For instance, when you have the curl of E equals 0, you have here a longitudinal field, right? Which can be derived by the gradient of a scalar function, the scalar potential, electrostatic potential. Then you go to the divergence equation, just replacing D by epsilon E. You're going to have the divergence of the gradient, which is the Laplacian. So you get the Poisson's equation. In magnetostatics as well, you have the fact that B is a solenoidal field, has a zero divergence. So B can be derived from the curl of another function, another vector, which is the vector potential. That's the intermediate quantity. Then we go to this is wrong here. I'm sorry. You go to the Ampere's law for stationary currents, right? Curl of H equal J. Then use the linearity of the field, the relationship between H and B through the permeability, and you prove that H equals curl of A divided by mu. You put that in this equation, then you have, given that in the divergent of the A equals to 0 in the Coulomb gauge for magnetostatics, divergence of A equals 0. We proved that before. Then we have this equation, which is let's say vector Poisson's equation for A, right? Is similar to the Poisson's equation, scalar Poisson's equation. The only difference is that phi replaced by A vector, rho replaced by J vector. Similar equations. We know how to solve these equations in unbound media. Let's just recall that because we are going to use that information. So equation like this in unlimited domain. That's what we are doing today here, right? We have a charge distribution in unlimited domain. So the solution is that integral expression for the potential. Epsilon goes to the denominator right there, right? In the same way, the Laplacian of A has a solution, which is the generalization of this one. The volume, right? The volume integral dv prime mu j divided by 4 pi x minus x plus. These are things that we derived before. Okay? So that's the question. That's for electrostatic and magnetostatic fields. What are the potentials that apply for time-varying fields? So let's revisit the equations. Let's rewrite Maxwell's equations. In terms of, we have homogeneous equations. In Maxwell's equation, we have equations that do not depend on rho or j. These are the homogeneous pair of equations that we have. And we have two other equations that depend on rho and j. These are the non-homogeneous equations. So the homogeneous equation is Faraday's law in differential form, which can be cast in this form here, curl of E plus dB dt equals 0. And the other one is the fact that B is solenoidal, has zero divergence. And the non-homogeneous equations are that specify the divergence of D, which is rho. Please notice the letters, the curly letters, right? Because we are talking about time-varying fields. And also Ampere's law. Curl another error here. It's amazing how I'm finding errors. I just made a quick review on my notes to see if there were any errors. I didn't see them, but I'm seeing now. So let me just fix it. This is the other equation. Let me see. I think. Let me see quickly here. Yeah, maybe I should already put that in terms of. Well, yeah, I can. Let me see here. Yeah, let me put the original equation here. That's the d dt, right? So let's fix that. So that's the Ampere's law, the generalized Ampere's law in differential form. The differential form of Ampere's law, right? So from this one, the fact that B is a solenoidal field, B can be written as the curl of A. Again, A is a vector potential. So we can define a vector potential for time-varying electromagnetic field, right? Because B has zero divergence. So we can put that into the Faraday's equation, which is this one here. We're going to have a curl of A. You can combine it. So you're going to have a curl of dA dt combined with E. We're going to have this field here. So we have a longitudinal field. So a field that has zero curl. So this field has zero curl. So this field can be written in terms of the gradient of a scalar potential function, right? So that's what we do here. This combination can be written. Let's keep the sign because the sign has a meaning. Let's not change now, right? Because we used that sign before. It came naturally. The static potential represented energy of a point charge per unit, per unit charge. And then we have the second potential is being defined here. So the E field now is obtained from the scalar potential, electromagnetic potential, psi, and the vector potential A. So if we find psi and A, we determine E like this. So in fact, the electromagnetic problem is going to be written in terms of differential equations for the electromagnetic potentials. We have two potentials to deal with, A and psi. So, so these are the electromagnetic potentials to obtain the EM fields. Okay. Let's assume that again, right? I mean, this we are going to see that materials have varying properties as a function of the driving frequency, right? If you look at if you have a broadband signal that has several frequency components, the permittivity and the permeability will very likely change with frequency. Okay, so at a given frequency you have one permittivity, at another frequency you have a different permittivity. So it's a function of frequency. We are going to assume, but there are regions in which this variation is very negligible. We are going to see that in the final lectures of this course. We're going to talk about the interaction of plane waves with, with materials. Very simple model. We are going to see how the frequency dependence appears. Okay, so but let's assume that we are in spectral regions in which, I mean, the frequency spectrum of your radiation field, right? You know the time variation of quantities, you know the frequency spectrum. And in this frequency spectrum, both permittivity and permeability are constant. They do not depend on frequency. That's is an approximation, but it's a very reasonable approximation in several different spectral regions. For a given application, you might have that condition. For instance, if you are in vacuum, that's really true. You don't have any material. Permittivity and permeability are those of the vacuum, right? If you have a material medium, even the atmospheric, as I mentioned before, if you have rain, pollution, and so forth, the permittivity and permeability might be frequency dependent, and then things we are going to talk about here might not apply, only in an approximate way. So, in fact, let's assume that the fields have a frequency spectrum where losses in dispersion is a concept in which different components of electromagnetic field travel with slightly different velocities depending on that frequency dependence of the permittivity and permeability. So let's neglect those effects. So we can write, even in the time varying situation, that the D curly, so the time-dependent D is epsilon times E, okay? You can never write that rigorously, okay? That is an approximation. Important to understand. This epsilon here has only meaning when you break the field into frequency components, okay? But now we are saying that there's no frequency dependency of parameters, so you can define this epsilon also in the time-varying case. It's a constant parameter. And B equals mu H. So we have LHI medium, linear, homogeneous, and isotropic. Now we can replace D and B into the equations. Okay. We have divergence of D. Just recall, right? Divergence of D equals to epsilon E, which is epsilon. Then you have minus nabla of psi minus dA dt. That's what we have. Is that right? I think so, right? Yes. Yeah, exactly. That's the definition. Then we plug into this equation here. That's what we get. So we have divergence of gradients of the Laplacian. Then you can interchange the time derivative with the nabla. Have ddt of divergence of A equals minus rho over epsilon. Have a second order differential equation that couples both psi and A. And this is a non-homogeneous differential equation. Okay. The second equation that we obtain is the curl of B, which is this thing here, right? Let's do it. So I have curl of H, which is curl of mu, B over mu which is equals to curl of A. Mu can be is homogeneous. You can remove from the equation. So we have this relationship. Generalized Ampere's law J plus epsilon ddt of E, right, which is minus gradient of psi minus dA dt. So here you can break this gradient of the divergence of A minus Laplacian of A, right? So I have this several terms here, right? Equals to J plus epsilon ddt. Then you have minus gradient psi minus dA dt. I give you time to work to rearrange these terms and show that it gives this result here. So just recalling, right? One equation was equation A. The other one is just doing these things I just showed you. If you work a little bit on it, you can rearrange terms. You're going to have Laplacian of psi here, Laplacian of A, second derivative of A, then you have a V here. The V is the velocity in the median, which is 1 divided by the square root of mu epsilon. Okay? If that was vacuum, we would have the velocity of light, speed of light in vacuum. Then you have this additional coupling term here, right? So we have the equation that looks like the homogeneous wave. I mean, the term that appears in the homogeneous wave equation. Then you have a non-homogeneity here. We have this thing here. Then you have this term that couples both A and psi. Okay. So that, I mean, formally, that's the way to solve it. Given rho and J, we have to solve these two differential equations to find the psi function, scalar potential, and A, which is the vector potential, right? The only problem is that those equations are coupled. It would be nice to solve them separately, to decouple them, okay? So we have some freedom of choice to decouple these equations. We notice that one of the quantities, which is the vector potential, has a curl that is tied to the B field, right? I cannot change the curl of A equals to B. It has to be tied to B, right? There's no way to change this equation. I cannot change that. But I can specify the divergence of A. Can be arbitrary. I can specify arbitrarily a vector A that has a curl that's specified, and I can specify independently the divergence. That's not going to affect the final quantity, which is B. Okay? So that's, when we do that choice, what is the divergence of A? Divergence of A. We are establishing a gauge. We have different gauges, which are, in fact, different specifications of the divergence of A. Well, one of the gauges is called the Coulomb gauge, which we already spoke about when we discussed magnetostatics. Coulomb gauge is that very simple one in which divergence of A equals to 0. And the question is, what are the consequences of using the Coulomb gauge? So let's just take a look here into the equations. When I put divergence of A equals 0, what happens? This term goes away. We have a simpler equation, which is Post's equation, in fact, right? And in this case here, I would have this term equals to 0. That's what I would guess. Okay, so what happens in Coulomb's gauge? Well, in Coulomb's gauge, I decoupled the differential equation that governs the scalar potential. We have a Poisson's equation, and when we set the divergence of A equals 0, we have an equation for A which is coupled with the solution of psi. Well, suppose that you solve for psi, we can plug that solution in here and solve for A, right? Let's take a look. Well, as I mentioned before, if I have an equation governed by this differential equation, we have already showed it that this, independent if the charge density depends on or not on time, well, the solution is this solution here, is that integral solution of Poisson's equation. This is valid for unbound domain. Why? Well, because if you have boundaries that impose conditions on the potential, then the solution is going to depend on those conditions on the boundary, right? We have showed that before. An integral solution for the potential, we have the normal derivative that comes up, right? And the potential value at the boundary that comes up. But if you have an unbound region, a source is going to produce a field that that vanishes at infinity. So that would be the solution. But the interesting effect here is that giving a disturbance that is produced at time t, the potential far away, there's several typos here. This is x prime, okay? So the solution, in fact, they're like this. Let me just draw the geometry here. We have a charge distribution at x prime, dv prime. Then we are observing the effect of a disturbance at point x. So we are determining. So each volume gives a small contribution. That's what that integral expression is a scalar sum of all the components. So what does it mean? That a disturbance at point x prime at time t produces far away, right? This distance here is magnitude of x minus x prime. Produce at a distance a potential which is given by psi, I'm sorry, that's electromagnetic now, psi of x at the same time t. So this solution doesn't have much physical meaning, even though it is an auxiliary function that will give the E and H fields which have physical meaning, right? But the potential itself doesn't have much physical meaning because there's no time delay between disturbance and the effect produced by that disturbance. There's no the finite velocity of propagation, which is the velocity of light, because if I do a disturbance here, in fact, physically, we know that the field is going to be felt only after some time that depends on the distance and the velocity of light, right? So the solution in the Coulomb gauge for the potential doesn't have the information on time delay due to the finite speed of light, finite value speed of light. So it's a solution that doesn't have much physical meaning. But this doesn't mean that E and H, which are the final quantities, don't have a meaning. I mean, this function with no physical meaning is used to determine those quantities that will have the information time delay. Okay? So recall that. A mathematical tool like the potential might or might not have some physical meaning, but the final quantity has to have a physical meaning, right? So in the Coulomb gauge, the scalar potential doesn't have the the time delay that has to be present in any event that relates cause and effect. There must be a finite time delay in the physical fields, but the mathematical function, the scalar potential in Coulomb gauge, doesn't have that. Okay. Okay, let's go on. It's possible to obtain a decoupled differential equation for A. Recall that the equation is coupled with psi. It can be solved after solving for this equation here. Suppose we solve for the potential, then we are going to obtain a solution for the A. I mean, that's evident, right? I mean, if you look at the equation here, if I solve for psi and calculate this thing here, I have a differential equation. But the fact is that this differential equation can be simplified, at least in a form. It's going to have a simple form that is related to the non-homogeneous wave equation. So let's break the J current density into two components, which we call the longitudinal component, JL, and the transverse component. So what is a JL, a longitudinal component? Well, JL is a vector that has zero curl. So it's a longitudinal field. It's like the electrostatic field, right? It's the one that has divergence, non-zero divergence. On the other hand, JT is the transverse field, or the solenoidal component, which has zero divergence. So we break J into two vectors. One which has zero curl, and the other has zero divergence. Recall that any vector field can be obtained if you know the divergence and the curl of that field. So that's essentially this theorem, Helmholtz theorem, in fact. Okay, so let's put that into equation. JL is the longitudinal component, so is a component that has divergence. So it's longitudinal. It can diverge from somewhere. Okay, so it has zero curl. The other is the transverse, which is the solenoidal component, like the B field, has zero divergence. Okay, so we can always decompose. Let's see why. Okay, let's calculate the. Let's recall Helmholtz theorem. J will be completely specified if I know the divergence and the curl. The divergence of A is the divergence, let's do it quickly, do it here. J equals to JL plus JT, right? If we calculate the divergence of J, well, divergence of the solenoidal component is zero. So divergence of J equals divergence of JL. Suppose that I know JL and JT, okay? So I know the divergence of J. Curl of J equals to curl of JL equals 0 plus curl of JT. So we have the specifications. If I know JL and JT, I know the specifications of divergence and curl, okay? So the fact that JL has zero curl allows me writing JL like the minus gradient of a function, right? That's the property of a longitudinal field. It's an irrotational field, has zero curl. So if I do that, you know, I go to this equation here. So I have divergence of minus gradient of f equals to the divergence of j. But recall that j is the one that's given. I know j, okay? So this is specified. I know rho and I know j. So this thing here is specified. So this is the Laplacian of f equals to minus divergence of j. So this is Poisson's equation in which the source equals to divergence of j. So we know the solution of that. F at point x time t, right, equals to integral of the divergence. This is calculated at the point x prime, so this divergence of j divided by 4 pi x minus x prime. So I found f, right? If I find f, it means that I solved for the longitudinal component, which is the minus gradient of f. So I solve for that. J is given, I determine JL. So that's the solution. It's going to be here. That's the solution. What about JT? Well, we have to find JL and JT. Because I'm breaking J into these two components, I'm just showing how to determine those. If I know J, JL is given by this. And JT, what is JT? Well, JT is solenoidal, has zero divergence, so JT can be cast as the curl of a vector, F. So curl of JT is curl of J, but JT is given by curl of F. So it's curl twice, curl of the curl of F equals to curl of JT of curl of J, right? So curl of F equals to let's see if there's something wrong here again. You know, just a minute. Yeah, that's correct. So curl of JT equals curl of J. If I plug JT here, curl of F equals that. Then we expand, as we did that several times, you know, curl of the curl is curl of the divergence minus Laplacian equals to this thing that's given. We know J. So again, well, we can do, I specify the curl of F by that. The divergence of F can be specified arbitrarily, okay? And more specifically, I can choose whatever I want without affecting the curl, right? So I set that to 0. Then I'm going to have a very simple, an equation that we are familiar with already, right? Curl of this vector equals to minus curl of J. This is the vector Poisson's equation that we know the solution in an unbound domain. So this is as if this was a source. That's going to be in the numerator of the integral expression, right? So there's no constant in front, so it's going to be the volume integral, F, it's going to be the volume integral of the curl of J divided by magnitude of the distance times 4 pi. So we found F. If we find F, we found JT. We have JT, okay? So that's what we have. We have the solution for JT. Okay? So in summary, given J, JL and JT are obtained. JL I just showed you. JL is given by this expression here. I know J, I know how to calculate this integral. And I know JT because I can, in principle, calculate this because J is given. I can calculate this one. So I have those two. So let's see what happens into the differential equation. Let's go back. Let me just show you again here. The differential equation, there's a coupling between A and psi. We want to eliminate that by defining those components. Let me pick this equation here. Sorry. Pick this equation here. I pick everything here. Copy. Let's move over here. Paste. Okay? So that's what we have, right? We have the term that's being coupled here is the term is this term here. Let's put it separately here. We want to see what happens to this equation after we define those longitudinal and transverse current density terms. So the term that we have here is ddt of gradient of psi. And recall that we solved for psi, right? Psi equals to dv prime sorry, not that. Psi equals to psi equals to psi was the Coulomb gauge. So the solution possible equation dv prime rho of x prime t divided by 4 pi epsilon x minus x prime. So I'm going to interchange here. It's going to be nabla of d psi dt, and d psi dt equals to the derivative of this term here. I'm going to omit the arguments, okay? So it's going to be integral of d rho. So let me tilt that. Recall that this is a time-varying function. 4 pi epsilon x minus x prime, and we have the condition, right? D rho dt is connected to the divergence of J, right? So d rho dt equals to the divergence minus of J, right? So when I put that in there, so I have that the d psi dt, we're going to write d psi dt equals to minus integral of divergence of J 4 pi epsilon x minus x prime, and then I have the nabla of that, right? I have if I put the nabla here, it's going to be something like that, right? And then we have 1 over epsilon. 1 over epsilon. Then we're going to have, let me do that, 1 over epsilon. That's what we got. So, so if we go into the equation that we just derived for JL, let's find, what is JL here? JL is somewhere in here. Where are my solutions? Oops. And for the solution for JL, because we can identify, where is it? Here. You see, JL is minus nabla. Let's put that there, so we can confront with the other one. So here, I put that down here. I hope it fits. So that's JL, right? So the coupling term, which is this term here, let's go back and look at the coupling term. Let me find here. Coupling term is right. Where is it? Here. So we have ddt, right? We have time derivative, we have velocity here, but we have a time derivative on a gradient of psi, right? That's what we're looking at. And we divide by epsilon also as well, right? I mean, this epsilon, let me see, let me go back, let me remove all these things here. We don't have that, and we don't have that. That's what we have so far, minus, right? So equals to minus, is equals to minus 1 over epsilon times integral nabla, right? So we can see that this thing here is equals to that one. So in fact, this equals to equals JL divided by epsilon. That's what it is. So that coupling term is simply the longitudinal component divided by epsilon. So let's put that in place of this thing here. This equals to this term here is 1 over epsilon times JL. And notice that I'm going to write here epsilon divided by V squared equals to, sorry, not epsilon. 1 divided by epsilon V squared, which is this factor here, this one with that, equals to mu epsilon divided by epsilon, which equals to mu. So the thing here is simply mu JL. Okay? So what happens? We have something like this. Laplacian of A minus 1 divided by V squared, second derivative in time, I guess is minus, right? Minus mu JL equals to minus mu J, which is the total current, right? So if move that into that, it's going to be Laplacian of A equals to minus mu J minus JL equals to minus mu times JT. So that's the equation we obtain. Now is a, formally, let's say, the coupled equation, which is this equation here. So that's a non-homogeneous, because this thing here, non-homogeneous wave equation. So in the Coulomb gauge, if we break the current density in terms of longitudinal and transverse components, we find that independent of that breaking, I mean, the potential, scalar potential is going to be solution of Poisson's equation. Vector potential is going to be solution of the non-homogeneous wave equation, in which the source term is the transverse current density component. Okay? We are going to see now how to solve this non-homogeneous equation. And we are going to show that the non-homogeneous wave equation has the correct physical meaning, let's say, for the potentials. It predicts the time delay between cause and effect due to the finite velocity of light. Okay? I'm going to show that. So let's move to that. Very well. Let's look at the Lorentz gauge now. It's a different point of view. I mean, we talk about the Coulomb gauge. We just set divergence of E equals 0. Let's go into Coulomb gauge. Sorry, for Lorentz gauge. I already did Coulomb gauge, right? So that's what happens. I mean, that's the original coupled equations without any specific choice for the divergence of A. Divergence of A. Right? That's the equation for A. Well, in the Lorentz gauge, we just simply obtain directly the non-homogeneous equation by setting this thing here equals to 0 by choosing divergence of A, not 0, but related to the potential by this relationship. That's the relation that defines the Coulomb gauge, and directly when we do that, we obtain a non-homogeneous wave equation in which the source element is the current density itself. Right? If we plug that into the other, the scalar equation, let me write down again so you can see it, right? So let's just recall the scalar potential has this form here, independent of the gauge, Laplacian of psi, plus the time derivative of the divergence of A, that's what we set to 0 before, equals to minus rho divided by epsilon. So in the Coulomb gauge, we have the divergence of A. Just put down. Divergence of A, Coulomb gauge, Lorentz gauge, plus 1 over v square d psi dt equals 0. So if we replace divergence of A by this, we are going to obtain some typo here again. Yeah, this is wrong here. Sorry, this is minus, of course. So if we replace divergence of A plus, well, this is right. No, this is correct. This is correct. This is not wrong. Divergence of A by minus 1 over v squared d psi dt, then we are going to have also a non-homogeneous wave equation for have a double derivative in time, second derivative of psi. So we have another scalar non-homogeneous wave equation for the scalar potential, and we have a non-homogeneous wave equation for the vector potential. Of course, if we solve for the scalar wave equation, you can solve for the vector wave equation. Okay. So now our equations in the Lorentz gauge are decoupled. We solve them independently, given not this one. This is the Coulomb gauge, right? So what I have is this. These are the differential equations that govern potentials A and psi in the Lorentz gauge. We have a non-homogeneous vector wave equation for A, related directly to the current density J, and the non-homogeneous scalar wave equation for rho. Why we say that's a wave equation? Because we solved that equation when the right-hand side was 0 before, right? We had the solutions, the propagating disturbance in space. And that's what we are going to do now, right? Let's consider a point charge. Let's solve the non-homogeneous wave equation. Let's consider a point charge in the origin of reference frame. In fact, I mean, we are showing Green's function for the wave equation. We are determining Green's function. When you solve the wave equation for a point charge, in fact, we are solving for the Green's function for either A or psi. Okay, so let's do that. So what's the density in this case? Well, we know, right? Point charge at x equals 0 has a density rho, which is q delta of x, right? Delta function. What does it mean? Well, it means that rho equals 0 for x different then 0, an integral of rho dV equals to Q in a volume if X inside V. Any volume, okay? Even the differential volume around the origin, we have that condition, right? For this situation, we have a spheral symmetrical problem, right? Quantities. Let's look at the, scalar wave equation. Sorry, equals to in this case, the problem depends only on R and T. Because the delta function here, in fact, is something like this. Delta of X equals to 1 divided by, I can write like this, 1 divided by R squared, right? Delta of R, that's the way is the delta function. If I integrate in the volume, it's going to give you 1, right? That's the way, that's the shape of the delta function. If I integrate in the closed volume, it's going to give 1, the result. So the potential function depends on time and only on the distance R, okay? If I make now, if I look at the equation, equals to what? Well, if R is different than 0, the right-hand side is going to be 0. So we have a homogeneous wave equation. Now we know that the potential depends only on R and T. We can use only the radial components, right? So Laplacian of psi now becomes that's what we have. Or alternatively, this can be also written as this is also, there's a second representation, something like this, d2 dr squared of r psi. Okay? So that's what we have. So the differential equation, right, wave equation, non-homogeneous, but for r different than 0, outside of the origin, the equation must be, in fact, 1 over r, second derivative, and then if I multiply by r, you're going to have this relationship here, minus 1 over v squared something like this, right? dt squared equals 0. Then I can call this function a function f. Let's define r psi, a function f. So we know that we have now d2f dr squared minus 1 over v squared df dr, df d2f dt2 equals 0. And we know that because we did that before, right? The function is a traveling wave. I have two choices, okay? We have the solutions that are in the form of a propagating disturbance, which is something like this. T minus or plus r over v. That's how it is. We derived that before in general, right? In an arbitrary direction. But if the quantities are only R and T, that's what it gets. The F plus solution is a wave that propagates away from the origin, and F minus is a wave that propagates towards the origin. So in fact, I mean, when we solve for the potential, we're going to have 1 over R, okay, Ft minus or plus R over V. So this, in fact, the function in radial, in spherical coordinates that has a 1 over R dependence is called a spherical wave. So for why? Well, because for a constant R, right, the amplitude is constant. So that's the origin. If I have a sphere, F is a constant. And also psi, right, is a constant. A spherical wave, the potential and the fields decrease. I mean, if we are propagating away from the origin, the dependence with the distance, besides the dependence with the F, but it has to change as the inverse of the distance. Because, let's say, if we're talking about the field, pointing vectors goes with the square of the field. And the square of the field goes with 1 over R squared. And the area increases with R squared. So the product is a constant. So it means that the power is conserved. That's the consequence. So every spherical wave, even for fields, has to have 1 over R dependence. That's the solution of the scalar wave equation away from the origin in spherical coordinates. So that's what we have, a solution in the form the minus sign has a divergent wave, plus sign a convergent wave. Okay, so that's the solution. Let's consider the divergent wave and see what the solution we have. Okay, so in fact it's like this. I mean, we are not going to have something going to the origin because nothing is produced, nothing is being produced away from the origin that gives some field that converges. I mean, the disturbance is in the origin, and the disturbance has to move away from it. So the solution we have to consider is the solution here, the divergent solution. Okay, so let's integrate the wave equation now, and let's take into account the existence of the singularity. So we have a Laplacian of psi minus 1 over v squared, the second derivative, equals to minus q delta, right? And now I integrate around the origin right? And this is going to give me minus q. I forgot the epsilon here, right? Over epsilon. So when we integrate, let me just outline that calculation. It's not complicated. It's just have to consider some terms here. So when we calculate the integral, we have two integrals, right? Let's consider the differential volume around the origin. So we have the integral of Laplacian of dv. We have Gauss's theorem is going to be used, okay? And we have this function here. So this integral here is approximately, the second one is easy, right? Because, I mean, this is going to be simply approximately the second derivative times the volume, second time derivative, and so if you calculate that, the second integral is going to be proportional to the volume. So it's going to give a 0 result. Have a second derivative. The volume goes with the cube of r, okay? And the function goes with the inverse of r, right? So this thing here is going to be something like r cubed divided by r, in which r is the radius of this differential volume. As r goes to 0, this goes to 0. So this term can be neglected. So I have to look into the first term here. So using Gauss's theorem, just recall that. Let's recall that. Volume integral of the Laplacian of psi equals to volume integral of the divergent of the gradient of psi, right? Gauss's theorem, so this is the vector, so it's going to be the surface integral of the sigma times gradient of psi. In fact, psi depends only on r, so this is equals to ar d sigma dot ar d psi dr, right? So you get a surface of a finite radius, and we calculate the derivative. So we're going to have a result that's going to be, this is r squared d omega, right? The radial component. And we are going to have, I mean, if you calculate the integral, in fact, it's going to be 4 pi r squared d psi dr in the limit that r goes to 0. That's what we have to calculate for the first integral. What is the limit when r goes to 0 of 4 pi r squared d psi dr? So let's calculate that. Right? Let's see what is right there. I didn't put it explicitly, but is this thing here equals to 4 pi r squared, right? The integral. D psi dr is constant, right? So that's what the integral is. This d psi dr. So that's what we have to calculate. Psi has this form here. D psi dr is this. Chain rule, okay, 1 over r, the time derivative. This is DDR, I'm sorry. This is DDR, okay. Another error there. So 1 over r, derivative of f, plus the derivative of 1 over r is minus 1 over r squared times f, okay. So then we have r squared times the derivative is going to be r squared divided by r, gives this term here. This DDR minus r squared divided by r squared is 1 here. Okay. In the limit, this is a regular function, right? It's not DDR. I don't understand why are doing and put this thing here. This DDR, not DDT. Yeah, I think there's a lot of typos here. So let me see. Yeah, limit of r times the f dr as r goes to 0 is 0 because f is a regular function. And as r goes to 0, this term goes to 0. So the first term goes to 0. Then we have the second one, right? after multiplying by r squared, the limit is simply going to be the limit of f as r goes to 0, which is f of t. So then we determine specifically what is f at r equals 0, f of t, which is q divided by 4 pi epsilon. So what we have is that we determined f of t, right? It's q of t divided by 4 pi epsilon, right? F of t minus r over v equals to q of t. So if you change the argument, you get minus r over v divided by 4 pi epsilon. Then we have the solution. Scalar potential in the Lorentz gauge equals to that's the solution. The scalar potential of a point charge in the origin equals to the retarded value of the static potential, right? We have a disturbance that takes place at t equals 0, right? It's going to be only when this argument goes to 0, which is after a time delay delta t equals to r over v, that the potential is going to have the value related to q of 0. When this argument is 0, is after a time delta t equals r over v. So it means that the disturbance propagates a time with a velocity of v, right? Disturbance is felt. I mean, the potential only feels the effect after this time delay r over v. So this solution for the scalar potential in the Lorentz gauge has a physical meaning differently than the Coulomb gauge. So we have the cause and effect, time delay, the retarded solution. In fact, it's usual to write the retarded time t prime equals t minus r over v in this solution. Okay, I'll always write like this: psi rt equals to q of t prime by epsilon r. This is the same expression for the static potential of a point charge. The only thing that we have to correct is the time delay, right? So what's the general solution for the non-homogeneous wave equation, both for psi and a? Well, we just break the source now into volume elements. Each volume contributes with a potential, which is the traditional one, right? Calculated at the retarded time. Well, this is r, in fact. Okay, this thing here is r, the magnitude of the distance between x and x prime. That's the r that appears. Same thing. Just change, the reference. Volume is at x prime, so the distance we have to use is x minus x prime. The q is the volume integral at time t. Then the potential can be written in terms of a charge density. We define this retarded time. Then you have a simple solution of the wave equation, which is the same solution that we obtained for Poisson's equation. Now, take into account time delay between cause and effect. So the time at time t, you have to calculate a retarded time t prime, right? With t prime given by this relationship. Solution for A is the same. We did that before. We break the potential into rectangular components, right? For each component, we have a non-homogeneous wave equation, which we already solved. For each component, it's going to have a retarded solution as well, related to the ith component of J. And we can now assemble all together, and we get the vector potential, which is the same solution we got for the stationary current for a magnetostatic case. The only difference is that the time here has to be taken into account the time delay. So that's the vector potential, the solution of non-homogeneous wave equation, general solution for unbound medium. Of course, if we have boundaries, then we have to go back to find, a general solution using Green's functions for the non-homogeneous wave equation. Then we have to do that. We're not going to do that in this course, okay? But I mean, this is the, you know the basics, right? If you know how to do for static fields, it's not difficult to do for dynamic fields. It's not the scope of this course to do that, but we have the basic formulation to achieve that, okay? So with that, we conclude today's class, and I hope to see you in the next lecture. Until then, bye-bye.